lot of uses for probability. And you can see in the first paragraph, like insurance costs. Like when you take personal insurance, like if you take an insurance policy out on a, say, spouse or on yourself, they actually have models to predict how long you will live. Okay, like it would be, yeah, it would be, which is oftentimes like they may require a medical report for you to apply for insurance, for personal insurance. Because what they do is they sort of take the family history, they take a whole bunch of factors and they come up with a probability. Now, obviously, it's going to be pretty low. Okay, but some are higher than others. You know, like if you have a history of, if you're a male, like say 50 years old, and your family has a history of heart disease, right? It could be harder to get personal insurance than say somebody who is, you know, 30 years old, doesn't smoke or anything like that, doesn't drink, no history of heart disease. But that's how they figure out the premiums to charge you, is they use probability models. And the more likely you are, I mean, because what has happened when they have to pay money? You've died. Okay, so they pay it to someone. So that means, you know, they have to figure out the probability of you dying. I know, it sounds more. Business decisions, medical procedures, obviously what you guys were just talking about, gambling, weather forecasting. Okay, probability is often used in the media. The probability of getting cancer from certain foods seems to happen weekly. You know, like this week you're going to get, you could possibly get big toe cancer from eating too much broccoli. I'm just thinking of that. You know, or you could get middle finger cancer from drinking too much iced tea or something like that. Anyway, I don't know why I said middle finger. That was no. I should have said pinky. Anyway, elections, another big one. Okay, the probabilities of one party winning. Like right now, you've got probabilities as who's going to win if election was called in Canada. And right now, the Conservatives seem to be quite well ahead. Okay, what happens up to the election, we'll see what happens. Anyway, probability, knowing probability helps you make better decisions, helps you analyze decisions. So the probability, the most basic formula, or basic definition, it's the chance of an event occurring. And an event is a possible outcome in a situation where more than one outcome is possible. So for example, if you flip a coin, there are two events that can happen. What are they? Heads or tails, right? If you wanted to find the probability of you flip one time, the probability of getting heads, well, it would be 1, because that's your outcome, your favorite outcome, out of 2 possible outcomes, right? So probability of an event, the general formula for simple probability, make sure I get this right. Number of ways an event can occur over total number of outcomes. So like I said, if you flip a coin, there's 2 possible outcomes, so the denominator would be 2. If you want to know the probability that you get heads, well, the number of ways heads can occur when you flip a coin is 1 time. So it's 1 out of 2. Now, probability always has to be from 0 to 1. And we can see that with a probability scale as well. It's just sort of common sense. Like, if I flip a coin, what's the probability of getting a jack? 0. It doesn't make any sense, okay? Because it's not one of the outcomes. But it can't be negative. The smallest it can be is 0, okay? If I have a deck of cards that has just one card in it, the Jack of Hearts, what's the probability that I'm going to draw the Jack of Hearts? 100% or 1, right? But I can't have more than 1. It's impossible. And you can show that using a probability scale. So you can see we just sort of draw a segment. 0 is impossible. 1 is absolutely certain. The closer we get to 1, the more likely something is to happen. The closer we get to 0, something is less likely to happen. So where would we put these? Using the letter A, where would you put the probability that the sun will rise next Sunday? Yeah, you'd put it right over 1. Because that's a surgeon. Unless those of you believe in some kind of Armageddon occurring before next time. Next baby born in your hospital will be a boy. Halfway through. Because the probability of getting a boy would be 1/2. The probability of getting a girl would be 1/2 because there's only 2 possible outcomes. This last one's a little gray. Somewhere in Manitoba, the temperature will reach at least 4 degrees once next year during the month of January. Where would you put it approximately? Like, could it happen? Yes. Okay, so it's going to be to the right of 0. Is it going to happen all the time? No way. Is it going to happen half the time in January? No. Okay, we saw what? This January, it happened a couple of times. I think we got, maybe one time we got as high as 4. So where do you think you'd put it? Somewhere around here? So maybe there. I mean, that one you can sort of argue that you could argue closer to 0, you could argue closer to 1/2. You know, you could say, oh, well, with global warming, it could be closer to 1/2. Or you could say, oh, well, it's Manitoba, where it freezes all the time, doesn't matter whether there's global warming or not, it's going to be close to 0. Notation using probability. This is how we show it. We use a capital P, and then whatever the event is, we're trying to find the probability of. So, like, for example, in 1A above, to find the probability of the sun rises in the east or sun rises next Sunday, it would just be P and then in parentheses, whatever the favored outcome is. Now, since an event either occurs or it doesn't, the probability of an event occurring and an event not occurring must add up to 1. Like, the probability, if you flip a coin, the probability of getting heads, let's say, is 50%. I'll use it in percent form, so it's 50%. Well, if heads didn't occur, it would be tails, and tails happens 50% of the time, and 50 plus 50 is 100% or 1. It's the same if you like roll a die. There's a 1 in 6 chance of getting a 3, and then a 5 in 6 chance of not getting a 3. So the probability of an event occurring and not occurring must always equal 1. Or it could look like this. The probability of an event not occurring is 1 minus the probability of the event occurring. And we saw that in stats last year. That was called the complement rule. So just as an example, the probability of it snowing on December 22nd is 1 out of 3, or 1/3. What's the probability of it not snowing? 2 out of 3, or 2/3. Because it would be 1 minus 1/3. Well, 1 is 3/3. 3/3 minus 1/3 is 2/3. Now, we haven't quite nailed this down yet, but probability can actually be expressed 4 different ways. Sorry, 5 different ways. I guess you could use a statement as well, use words. But we're going to focus on the numbers. Ratio, fraction, decimal, percent. Well, fraction, we have a numerator and denominator. Decimal, we use a decimal point in there. Percent, we have the percent sign. Ratio always uses a colon. And it's going to look like that. If you remember. I mean, that's what we're going back to middle school there. That's probably, ratios can be written as fractions too. So I'm going to say this as well. Either of those can be called a ratio. Okay. Example 3. You flip 3 coins at the same time. What's the probability that they land all heads? Well, first of all, we're going to have to figure out what are the total number of outcomes. So what can you get when, like, what are all the possibilities you can get when you flip 3 coins? Well, heads, heads, heads. We could get all heads. We could get all tails. What else could we get? 2 heads and a tail.
2 tails and a head.
2 tails and a head. We could get heads, tails, or heads. Actually, we should probably do this in some order, right? That would make more sense. So just keep what you've got. Let's start with all heads. So we've got heads, heads, heads. Or we've got heads, heads, and then the last one is tails. Or we've got heads, and the next 2 are tails. Or we've got tails, heads, tails. Or 2 are heads. Is there another way that we can, so we could get HTH too, right? So there's only one way to get 3 heads. TH, what about THH? I'm trying to think of all the ways we can get at least 1 head. Isn't that right? THH? Yeah, T. So 2 heads, we could get HHT, HTH, or THH. 1 head, we could get H at the beginning and 2 tails, H in the middle, or H at the end, right? So TTH, I think that's what you said. Well, those are all the ways that there's at least 1 heads. But there's still one other option. There's no heads, tails, tails, tails. So the number of outcomes is 8. The number of ways of getting 3 heads is 1. So as a ratio, we would write this or this. And we would say 1 to 8. Fraction, obviously, would be something like that. So like we could either say it as a ratio of 1 to 8, or we could say it like 1/8. Okay. 1/8. Decimal, well, just divide the fraction. You'll get 0.125. Percent, take the decimal, move the decimal point 2 over, 12.5%. So for the next example, using the same scenario, flipping 3 coins, find the probability that 1 coin lands heads. So we know that the denominator is 8. What would be the numerator? 1 heads. Doesn't say at least 1 heads, it says 1 heads. How many situations is there only 1 head? 7, only 1 head. 3, right? Here, here, and here. Because the other cases, it's 2 heads, and then the final case, it's 3 heads. So go ahead and write those 4. Now that you know the numerator and denominator, you should be able to do these. Because we discovered that there are 3 ways. So your ratio would be 3 to 8, or written that way. Fraction would be that. Decimal would be,
0.375.
which means the percent would be,
Scenario last year where in the state of each.
yes, yes. So, I mean, like, it's an interesting question. So if I did ask you that, what is the probability that at least one of them would be heads? So it'd be 7, right? Okay. So let's just look at some different situations here, different problem situations, where we're given a scenario, we're asked to find probability, and then we're told how to express it. So a city is interested in knowing how many of its roads and sidewalks needs to be repaired. City engineer randomly inspects 38 roads, finds that 4 of them need to be repaired. Also finds that 6 out of the 45 city sidewalks he inspects or randomly need to be repaired. What's the probability a city road needs to be repaired as a decimal? What would it be as a fraction? 4 out of 38, and then we just have to change that to decimal. Let's go 2. 0.11. Good. What's the probability a city sidewalk needs to be
Repair of, speak. Well, that would be 6 out of 45, and then change that to a decimal.
One.
0.13.
So how do the roads and sidewalks of the city compare in this respect? Pretty even, but it seems city sidewalks need more repair. Not that much. I'm thinking this is not a city project. Okay, another example. During the regular playing season, 10 out of 84 games in a particular soccer league go into overtime. What's the probability a game will go into overtime? And it doesn't say how to specify. So let's start with the easiest one, fraction. 10 out of 84. Now, here's the nice thing. You don't have to reduce these. Okay? Usually with probability, I mean, you can reduce it, but a lot of it's not necessary. Okay? So based on this, based on the probability in the regular season, and there's 16 playoff games, how many would you expect to go into overtime? How would we figure that out? Well, this is the probability of going into overtime, right? Maybe it might be easier to express it as a decimal. Zero. 0.12. Doesn't that mean that 0.12 of the 16 playoff games will go into overtime?
And of means multiply. So all you do is you take the probability you got A, and you could have kept it as a fraction. Multiply by 16.
Now, you're not going to get a nice whole, clean whole number, so we're going to have to say approximate. So when you do 0.12 times 16, you get 1.9, so approximately 2 games you would expect to go into overtime. Based on the regular season probability. Do you think those probabilities are going to be the same? Why? Remember, we're talking about soccer. Remember, we're talking about sports playoff. Do you think more will go into overtime or less? Okay, that's one way to argue it.
Can you explain, and who has to be in a math quiz, or can I?
No, just sort of think like you can, I mean, there's really no correct answer here. I mean, it is possible to say, you know, well, there's 84 games in a regular season. So maybe 10 out of 84 was low for that season. Maybe it's more because there's more games that are played, whereas there's only 16 played. So you could argue that way. How could you argue the other way?
I'm thinking, you know,
I mean, playoffs, much more and intense. So they're probably playing tighter in playoffs, regardless of the sport. So that may increase the probability that games will go into overtime, which is, I don't know, I'd be interested to know what the case is with hockey, with the NHL. How many games go into overtime versus, because it always seems like come playoffs, a lot of games seem to go into overtime.
I would say, well, in the NHL, it's a different game.
Absolutely. Yeah, I mean, the stakes are much higher. Okay? So I'm just going to sort of leave that one open.
So either or.
Yeah. Because it's really, I mean, you know, you can, or I'll just say you can argue both sides. Last example. We've got a bar graph. Television viewing habits of students in 3 grade 11 classes. So our x-axis is number of hours per week, and our y-axis is the number of students that watch TV in those number of hours per week, and it's presented to us in a, what would you call this?
Wait, yeah.
Oh, do we remember? Nice. Histogram. I know, we talked about that in stats. Okay, so determine the probability of each of the following events. A student in these classes watches 12 to 16 hours. Well, how many watch 12 to 16 hours? 10, but now we have to figure out how many students total, which means I have to add all of these bars. So 5 plus 7, 12 plus 8, 12 plus 8, plus 10, 30, plus 16, 46, plus 12, 58, plus 10, 68, plus 8, 68 plus 8, 76 plus 4, 80 plus 2. So I think we're 82.
My math got better.
Is that what I got in my, I just want to see my. Yeah, 82 is good. And remember, like you can change it to decimal, you can leave it as a fraction. You can reduce it if you want, but you don't have to. What about the probability between 16 and 28? So that means 16 to 20, 20 to 24, and 24 to 28. We have to add those 3 bars. So that gives us 28, 38 in those 3 bars out of the 82 in all the bars. For part C, watches more than 4. So that means all these bars. But is there a quicker way? How many are there total? 82, and yet 5 of them are only under 4. So 77 out of 84. That 82, pardon me. That would be a better way. Or a more efficient way to get to the answer. And finally, based on the probability calculated in this data, how many grade 11 students out of 500 would you expect to watch 12 to 16? Well, 10 out of 82 watch 12 to 16 right now. I can change that to decimal if I want to, and then I just times by 500. And that will give me my approximate number of students.
Oh, wait, I'm 61.
61.
Oh, okay.
So just sort of a summary of what probability is, how we can show it, what probability values range from, and then how we can express them, and then how we can use them in some problem situations. Next thing we're going to talk about, which we actually didn't in stats, is odds. Because we show it slightly differently. It's based on probability, but we express it slightly differently. It's just not the same kind of fractions and ratios. Anyway,